Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. So I'd like to kindly request our members to subscribe, engage us in the comment section, and also ring that notification bell to be getting various discussions on different topics in mathematics and sciences. I'll be putting a link of various discussions in terms of a playlist in our description boxes of various videos. So kindly check in case we need clarity on our various topics so that we can be able to be getting those specific updates. So our discussion today basically is going to be relying on the properties of and the characteristics of transition elements, and this is going to be a complementary video that is going to assist us of course on top of the previous one that we have done on the concept of transition elements. And in our last discussion, basically we had given two definitions for the common one, and according to the IUPAC system of the definition of a transition element. So the first one, we had said that transition elements are elements that are going to contain the D or F shells, D or F shells, either in their elemental form or in their in any of their commonly occurring oxidation states. And of course, according to the IUPAC system, we have defined the transition element as an element that is going to contain partially filled D or F, of course, subshell. And this specific use of term, of course, differentiated this particular definition of a D or rather a transition element. And we are given particular examples for zinc, cadmium, and mercury. And of course, the three assisted us distinguish between elements which can be classified as either a transition elements or not, according to the two particular definition for the common one and IUPAC definition. Now, in this particular case, I said that elements are going to consist of this specific shells for the D and F. And of course, if we consider the case of zinc, which we have listed, I can give this particular subshells which are of concern. So we had the last two being given in terms of the 3D10. And this, of course, was particularly we had given this one as argon, as shorthand form of this specific electronic configuration, which had given us this specific definition or rather configuration for zinc. So in this particular case, we had said that according to the IUPAC system, there was going to be a violation of this particular definition if we consider the D. This particular element consists of the D, of course, a subshell, but this specific subshell is going to be filled up, so therefore it's going to violate this particular definition. But according to the first definition, we're going to see that the element is going to consist of the D subshell, and therefore it's going to be classified as, of course, a transition element. If we consider for the case of, if we look at particularly copper, so I'm going to give this one in terms of copper. So this is going to be 4s, then we are going to have 2, 3d9. So if we consider this one particularly as an ion of copper, we are going to have this specific. So if we consider this one as an ion of copper, which is going to be given as this one, we're going to be concentrating basically on this D, of course, D subshell. And of course, this is going to be partially filled orbital, since it's going to consist of 9 contrary to the 10, of course, electrons. And therefore, that's going to be classified, it passes as a transition element. But if we consider this specific case, we're going to have this specific organization of the 4s1 and 3d10. So this specific configuration is going to give us the D subshell being filled, and therefore this is going to be a reference for the copper positive ion, and this is going to be disqualified. So this is going to be disqualified as a transition element in this specific case due to the configuration of this particularly fully occupied D subshell. Now we're going to look at various other forms which we are going to come across in these two specific definitions. But of essence for us, we're going to rely really on even those ones which have just given in terms of the IUPAC system. So we're going to consider them as transition elements according to this specific definition. Now, in this particular case, I'm going to look at various properties. In our opening statement, I said that basically these transition elements are going to be classified as, or rather they're going to be classified as metals. And of course, we're going to see that all of them are going to be solid in solid form, except mercury, or solid except mercury is a liquid form of metallic substance. So we're going to see that it's a heavy metal which is going to be liquid in, of course, in its particular state. Therefore, we're going to see that these are two specific differences, or rather some of the characteristics which we're going to see being displayed by transition elements. And for them being metals, these are going to exhibit the metallic character of being strong, hard, and of course they're going to be good conductors of both heat and electricity. And then we're going to see also that among other characteristics of being shiny and of course malleable, ductile, they're going to be having those particular characteristics. Also, we're going to see that many ionic and covalent compounds that are going to be formed by these transition elements in one or in not either in one or some of their states, of course, are going to be having some kind of a color. Or we can particularly look at a specific example, but we can have these ones. So the ionic compounds and of course the covalent ones, which are going to be formed by these specific compounds, of course are going to be colored in one, if not all, their oxidation states, as we're going to see. Now, I've mentioned the concept of oxidation states. And these particular oxidation states, as we said, they are going to be displayed, and the transition elements are going to be having a wide range of these specific oxidation states. Now, the color that's going to appear from these many ionic compounds and covalent compounds that are going to be colored either in one or their oxidation states are going to depend on the absorption in the visible part of the, of course, the UV region, or the visible part of the electromagnetic spectrum, or the UV region. So this is going to be depending on the absorption characteristic of this specific element in the visible or the UV region of the electromagnetic spectrum. So therefore, we're going to witness some of the colored compounds, and we're going to be explaining as to why those specific compounds are colored. So in this case, we can give an example of those specific oxidation states which are colored. And in this case, I'm going to depend on this specific, or just illustrate using this specific element of nickel. So we shall have this complex ion of nickel given as this. So this is going to be positive. And then we shall have this one formed assisting this one. And then we shall have this one perhaps using this particular compound. So we're going to have this one. So this is going to be blue in color. So this is going to be green. And then the last one is brown red. So the different compounds are going to exist, or these various oxidation states are going to be of course, transition elements are going to exhibit the concept of colors, and this is going to be realized due to their absorption in the visible or the UV region of the electromagnetic spectrum, as I've mentioned. So in this case, this is one of the characteristics of compounds having ionic or covalent, of course, forms having some kind of colors. And these are some of the examples which we are going to be seeing being displayed. So this is going to be specific, whereby we're going to have the D block elements showing this specific colors due to the what we call the change transfer, or the of course they're going to be realized due to the transition of the D to D transitions and the F to F transition, which are particularly specific. So in summary form, I've said that the D block elements are going to exhibit this concept of a color due to the D to D transitions, whereas we're going to have the F block, which are lanthanides and say actinides elements, having this color due to F to F transitions given as such. So they are going to be specific according to these specific subshells, or the kind of a transition that is going to be appearing for these two specific subshells that I've mentioned for F and D given in that particular case. But we're going to see that for the F block elements, they're not going to be affected by these specific complex formations which I've given, for example, for the three ions. And in that particular case, then therefore we're going to see that the color is going to remain the same for some specific ions. And if we give an example of this one, which is a zinc sulphate, which is going to have this specific arrangement, so we're going to see that this particular element is going to be colorless. So we expect a D to D transition to appear where this specific orbital is partially filled, and if it is fully occupied or having of course no, or it's an empty subshell like the tin oxide. So in this oxidation state, we're going to have the D orbital having 0 electrons. Therefore, this is going to be as well having a colorless, of course, kind of a formation given as such. So that's going to be depending on the particular ions which were said. But as we said, if there is a transition between the D to D transition, these are going to exhibit colors for a range of elements of the D block and for F block in that specific respect. Now we're going to look at another characteristic of these specific elements. And in our introductory part, I mentioned that basically for us to discuss this range of elements, I'm going to categorize them. Now from scandium as the first group of elements which I'm going to regard as the scandium group. So we're going to see that across this specific, of course, a period, we're going to have a range of elements going up to perhaps, if I'm not wrong, that's going to be going to zinc. So all through to from zinc, scandium to zinc and copper, we're going to have this specific arrangement regarded as a series. So I'm going to regard this one as a series. But down the group to yttrium, lanthanum, up to the last element in that specific case, we're going to regard this one as a group. So down the group, I'm going to regard this one as a group, but across this one, I'm going to regard them as a series so that we are in conformation with this specific trends. Now, in the series of scandium, we're going to see that some elements like, or the various oxidation states like scandium 3, and then we're going to have titanium 4 given in this specific case, and then we shall have this vanadium 5 and manganese 7 are given as such. These are going to have the empty D subshells, and they are expected to be colorless just like the previous two examples which I've given. However, we are going to see that particularly for this last oxidation state of manganese, this is going to be purple in color, and we're going to give an explanation for that so that we are able to understand in case we come across such a kind of characteristics in our various oxidation states of other transition elements. So this is going to be, of course, purple in color, and particularly we can give these oxidation states for the manganese 7 given as such. So this is going to be a purple ion, yet it does not have what we refer to as the D to D transition. So I said that this is going to consist of an empty, of course, it's going to consist of an empty D shells, and therefore it's going to have it's not going to experience the D to D transitions which I've given on the board. But the presence of the color is going to be realized due to what we refer to as the change transfer mechanism. So we're going to have the change transfer mechanism. So I hope my handwriting is legible. It's a mechanism. So the explanation for the presence of this colored, of course, compound or ion or oxidation state is not realized due to the D to D transition, but of the change transfer mechanism. Now we're also going to see that the concept of polarity is going to be affecting the intensity of these particular colors, and we can give an example of the silver ion, which is going to react with the halide in this specific order. So we shall have this compound of silver, chloride, silver bromide and silver iodide. Now in this case, we're going to have this particular case for the silver ion. And if we can illustrate it in terms of a polarity, of course, we're going to see that the silver ion, for instance, is going to bond with the bromide ion. And we're going to have some specific charge which are going to be realized around that particular, or the overlap of this specific, of course, charges are going to be realized in some way. And there's going to be, of course, the silver is going to be pulling some charge which are going to be giving rise to some observed colors. Now, in terms of polarizability, we are going to see that or the intensity of these specific colors which are going to be appearing can be explained due to the polarizability of this particular, especially ions which we're going to see. So if we consider the iodides, the bromides, and the chlorides, we're going to have them, of course, increase in polarizability using this specific trend. So the more polarizable, and of course, an ion is, then therefore that's going to be more colored. So in this case, we expect that the silver iodide is going to be more colored compared to these other, of course, silver, of course, compounds which are going to be formed. Now, in this particular case, we're going to see that the transition elements, they're going to form a variation of oxidation, or of a number of oxidation states. And of course, we can as well see that these particular transition elements can utilize the S and D, of course, electrons for bonding. Now, we're going to use various examples in this particular case, especially for the last statement, which I've said we can use an example of a scandium that is going to have the 3D1 and 4S. Two electrons. Now I've said that some transition elements, or the transition elements, can form a variable oxidation states, and they can use as well the S and D electrons for bonding in this particular case. Now we're going to see that particularly for the series and the group which I've mentioned. So I've mentioned the scandium series, which is going to run across to particularly across copper to zinc, and then we are going to have this specific series run through yttrium down the group. So basically this is going to be a series, and then I'm going to regard to the vertical, of course, which is a column as a group. So therefore the oxidation state is going to be progressively stable as we go across the series, and therefore we're going to expect the stability to increase in that particular order for various range of series which I've mentioned, of course, for the various transition elements. Now we shall look as well as other compounds which are going to be having particular characteristics. Now in this case, if we consider the particular compounds for the first row, the highest is going to be, if we look at the group 7, we're going to have manganese, of course, rhodium, and then we shall have this specific element of osmium. We just confirm from my... Or perhaps we shall be mentioning that one on the concept of stability in our different discussions, so that it's able to be, or it's more elaborate in giving it more time. So other properties which we're going to witness for this particular compounds are lower oxidation states. And in lower oxidation states, these specific compounds are going to exist as single ions. But in high oxidation states, these specific, of course, compounds are going to appear covalently bonded as a covalently bonded element to either oxygen or fluorine. So we're going to have an example of this one. For instance, if we consider the case of manganese 7, we're going to have manganese 7 given as such, and then this is going to be manganese 7. So for manganese 7, it's going to exist as a bonded compound, and not in the form of an ion or a simple ion, which we have said, which is given as manganese 7 positive. So in this case, this is an ion which is going to be having what we call a high oxidation states of a 7. So therefore, it's going to appear as a bonded compound, contrary to the oxidation state which we have given in this particular case. So the rest of members of the transition elements which we can consider for this particular case for having this, or rather having this specific compounds appearing as covalently compounds, the compounds of vanadium, So we're going to have a vanadium 5 appearing as a covalently bonded compound, and also for the chromium 6, which we are going to give in this particular case. So among others, we are going to witness some of these compounds of a high oxidation states appearing as covalently bonded compounds, contrary to the ionic form, which are going to be experienced in lower oxidation states. So these are some of the characteristics which we are going to witness for the transition elements. And in some of our discussions, of course, I'm going to put a link of various discussions we have on different, of course, characteristics of the previous S and D block elements. And that's going to assist us contrast them with the transition elements in that particular case. So check our description boxes for various links of other videos, and also ring that notification bell to be getting updates on various discussion we have in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.